Okay, welcome everyone to our second class. I saw there were plenty of assignments pushed to the repo already, which is great. We will do a little bit with them later in class. So I wanted to start today just with a brief review of the things that I hope you feel you've learned from the first week of class before we get into the second week's worth of stuff. So it's a lot of stuff that I've put on you in your first week here, starting with basic data manipulation and exploration using R and dplyr. We'll be doing plenty more of that, but you've gotten your start at least from loading data, generating random numbers, and generating some basic plots. I think you have also cloned the GitHub repo, and most of you have managed to contribute to it as well through a direct push. And you've made assignments either in R or R Markdown. By the end, you'll be using R Markdown. It's fine if you're not using it yet. And then as far as statistics, we got started by defining random variables and the idea of distributions and getting a little bit of visual familiarity with some important random distributions, starting with the normal, Poisson, negative binomial, and binomial. There was one more thing from the last class that I just wanted to give you one slide on because it'll be important for today's class that we didn't go over yet. And that is just a little bit more detail about the normal distribution, which is a very important distribution in all kinds of applications in statistics. It is really surprising how frequently the normal distribution turns out to be useful. Without getting into the mathematical definition of it, the things that you really need to know about the normal distribution are, one, that it is bell-shaped like this, also called the bell curve or Gaussian distribution. It's defined by two parameters, its mean and its standard deviation. And when we're talking about a population, we'll use Greek letters, mu and sigma. When we use samples, we're going to use Roman numerals instead. But the mean for any symmetric distribution, including the normal distribution, the mean is at the center. And coming out from there, we have non-zero probabilities all the way from -infinity to infinity with defined probabilities of having observations within any interval along that curve. So the ones that we tend to remember are these few important ones. There's actually a name for these. So within plus or minus 1 standard deviation of the mean, you have 68% probability of making observations, or put another way, out of a large sample, 68% of your observations will fall in that area. So if you're talking about some standardized exam scores where they're graded on a curve, say with a mean of 70 and a standard deviation of 10, then you'll have 68% of the test scores between 60 and 80. You'll have 95% of the test scores between 50 and 90, and then 99.7% of them between, I guess that would be 40 and 100. There's actually a name for these three numbers. It's called the empirical rule. I mean, in any distribution, you could define probabilities along some set areas like this, but these numbers come up frequently enough that it gets its own name. And the one that you will use over and over in practice is this plus or minus 2 sigma, 95%. Can you have it? You can probably imagine why that's an important region of probabilities. It's important really only because of custom that people often talk about 95% confidence intervals and about a rejection of a null hypothesis with a p-value of 0.05. In both of those cases, in the case of a 95% confidence interval, you're going to give the region in which 95% of a probability falls. We'll get into confidence intervals, I think, in the next class. And in the case of null hypothesis testing, you talk about the probability in the tails where 5% of the probability lies. So in both of those cases, the key region of the distribution is plus or minus 2 standard deviations. It's actually 1.96. And when I'm doing calculations, I often end up typing in 1.96. It's not exactly 1.96, but it's very close. So if you know those properties of the normal distribution, you know what the mean is and the variance, the definition of the variance. The mean is just, you add up all of your values and divide by the number of values you have. The variance, similar, except that you subtract the mean from each one of them, so it gives you a measure of the spread. It's like the average squares of how far each observation is from the mean. And I'm using a capital N here and using a definition that corresponds to a population, because we haven't talked about samples yet. These are a little bit different when it comes to samples. All right, so for today, I'm going to introduce to you sampling and strategies for sampling. Well, we already did identify properties of the normal distribution, and then I will introduce to you the central limit theorem and a little bit about the t-distribution as well. And this is all from chapter 1, about the first half of chapter 1 in the book. So our primary purpose in inferential statistics is to take an incomplete amount of information from a population, because we can't observe the whole population, and make inference from some small amount of the population. So here is an example, actually fairly small population. There are only 12 individuals in it, where we're taking a sample of size 4 from it. And this would be an example of a simple random sample where every individual in the population has an equal probability of being selected, and then we use a random number generator to simply select our sample of a desired number 4 out of the population. So some things to note about this. We have enumerated the entire population here, and that is what we call the sampling frame. That means that we know who has a finite probability of being sampled. If you don't know that, then it is difficult to say that you are taking a random sample and that everyone has an equal probability. In order to do a true random sample, you actually do have to somehow enumerate every individual in your population so that you can select from them randomly. There are many cases where you don't actually do that, but it is less clear than what your sampling probabilities are. This is a key second point here, that the sampling probability of every individual in the population must be non-zero. If there are individuals in your population where there is no possibility of them being sampled, then they may as well not be in your population. And I'll talk a little more about this, but this introduces what we call selection bias. And finally, we must know what the sampling probability is for every individual in the population. We must be able to write down what that probability is. It doesn't have to be equal, but we have to know what the probability is. So the population distribution, we can describe and summarize using parameters. If it's a normally distributed observation in the population, then we would describe it by the mean and the standard deviation. Those two parameters would be enough to completely describe the distribution of something like test scores in the population. And then individuals in the population, they can be referred to as a record. And on those records, we make observations. When we draw a sample from that population and calculate something from that sample, such as the mean or the standard deviation, when it comes from a sample, it's called a statistic. So mean and standard deviation, if it's of the population, it's a parameter. If it's of the sample, it is a statistic. And then we can use that statistic to in turn make inference about the population, and specifically about the population parameters. So mean and standard deviation of a sample, those are statistics, which we could then use to make inference about the mean and standard deviation as parameters of the population. This graphic here summarizes the way we use consistent notation to help keep those separated, because it can be confusing if you just say number, or you say mean or variance. It's not clear whether you're talking about the parameter or the statistic. So we tend to use capital N for a population, lowercase n for a sample. We use the Greek letters, mu and sigma for the population, and Roman letters for the sample. And this goes for other distributions as well, whether it is Poisson or whatever else. This is a very common convention to use. There are many sampling strategies, and I just want to make you generally aware of them. These can become important if you're involved in experimental design. They can be important to know about as a data analyst as well. You'll find that most, I think, I expect as people analyzing biological and genomic data, probably most of what you will encounter you will be under the assumption that it is simple random sampling, that it is a sample where every individual in the population had an equal probability of being selected. This is the easiest type of data to analyze. It's not necessarily the most efficient, as we call it, though. Often a stratified random sampling is better than a simple random sample. This is a strategy where you predefine so-called strata in your population, and singular stratum. A stratum is something which distinguishes individuals in your population, and it could be almost anything. So as an example, if you have in your population old and young patients, male and female patients, a stratified random sampling approach might be to call every individual either an old man, old woman, young woman, and then select an equal number from each of those four groups. That would be a stratified random sample. And it is often better because it reduces your amount of sampling variability and allows you to make more accurate inference based on the same sample size. And it generally does not complicate analysis either. So if you are involved in designing an experiment, you may wish to consider doing a stratified random sample. Cluster random sampling.
Is the sample size to be the same for each stratum? So if the stratum represents different categories,
right,
which are differently represented in the population, so the stratified random sampling should be.
It's a good question. Do the strata should you have the same sample size from each stratum? And the answer is not necessarily. It depends on your objectives. So one objective of stratified random sampling may be to obtain proportional representation, in which case you might choose sample sizes that are equal to the proportions of individuals in each stratum. So they might not be the same sample size. Another objective might be to select equal numbers from each of these. One important example of that is a case control study where you have people with disease and healthy people. And for making most efficient use of your research dollars, where you want to compare diseased and healthy people, if there are only 1% of people in the population with disease, you don't necessarily want a simple random sample that's going to have 1%. You know, if you have a sample size of 100, you only have one person with the disease, or maybe nobody if you get unlucky. You would, in this case, do a stratified random sample where you take an equal 50 people with disease and 50 healthy people. So it is not proportional to the population. You're overrepresenting one group and underrepresenting another intentionally. So there are important study designs that use stratified random sampling with non-proportional representation from the strata. That's still a random sample, but it's a stratified random sample, a type of it. And maybe I will, in one of our next classes, I'll put in a slide on some of the important epidemiology study designs, just so that you've heard of them at least, because within these there are a number of different study designs depending on whether it's experimental or observational, what type of observational study it is. These are good to know about. Thanks for the question. Cluster random sampling is something that I suspect you're unlikely to come across if you're not working in epidemiology or randomized trials. This is a strategy that is popular in cases where it's not practical to do a simple random sample or stratifying based only on individual characteristics. And it's a strategy where you have clusters of individuals. You first randomly sample an entire cluster of individuals, and then you sample individuals from within each of those clusters. So you'll have entire clusters of people where no one gets chosen. But that's okay because they still had a non-zero probability of being chosen in the design of the experiment, and you know what the probability is, so it's okay. A couple examples of where cluster random sampling is done are in health studies across some large geographic region where you're going to select individuals at random, going door to door and trying to find them. It might not be practical if you're trying to do this across all of Italy and you've randomly selected people across the entire country. What you might do instead would be to randomly select several regions of the country first. And then within each of those regions, you have a higher proportional representation within these regions. So you're able to focus efforts on a smaller amount of geographical areas rather than across the entire geographic area. That's one example. Another example are randomized trials where an intervention is performed at the level of schools or something like that. You want to find out the effectiveness of malaria prevention education done through. You can't do an intervention like that, like introducing malaria education to individuals. You're going to do it to entire schools. You could design a randomized trial where you have 40 schools in the country. You select 10 of them for your intervention and 10 of them for a control group, and continue then by sampling individuals from each of those schools. And then more generally, complex sampling are designs where you have unequal sampling probabilities. And there are several ways that can happen. It can happen through stratification. It can happen through desire to overweight certain individuals who have a small prevalence in the population. So many health studies, if you have a population that is, say, 90% white, 5% black, 2% other, and you want to be able to determine something about each of those groups from your study. A simple random sample isn't going to accomplish it, because you'll have than you need of the majority population and not enough of the others. So you will overweight certain demographics in order to have enough representation to be able to make some conclusions about them. And that's a form of complex sampling. All of the national health surveys in the US use some form of complex sampling. Finally, what we call convenience sampling, which is basically whatever records are easiest to observe. Can you think of any problems that might arise from this type of sampling?
We're not specific at all. We're just looking at something particular, excluding a large majority of events.
Yes, that's right. Your majority of events which may have zero probability of being selected And there's no guarantee that this sample that you have will be representative of the population. So if you're using statistics, then you're probably going to try to make inference about a population from them, but without knowing how it represents the population. It might actually represent some very small fraction of the population. It sounds like, why would you do this? But the reality is, in genomics studies, in observational studies of cancer, this is what almost every study is. When you read a paper about, I don't know, a group that has studied 100 tumors, and they've found that those that survived for 5 years or more differed in these genes, these pathways, from those who died within a year. How do you think they got those 100 tumors? Do you think they did it by creating a sampling frame of the population of cancer patients? No, they went to their tumor biobank and they saw whatever tumors were available and whose patients had signed an informed consent, and they used them. Sometimes there will be some extra effort made to say we selected from all of the patients over this period of time at our hospital, so that's something. Or they might say this percent of the patients we had tissues available and had informed consent, but probably not. Probably you have no idea how much of even the patients from that hospital are represented in this sample. So I think this is an issue with genomic studies, and probably part of the reason why it can be so difficult to achieve reproducibility across different studies if you have unrepresentative samples being studied. It's hard to say, and it depends. Sometimes a convenience sample might be representative anyways, but it's hard to know.
But probably there is, so the convenience sampling, maybe that it is possible and it is not negative if you are interested in other questions, like understanding the difference between different tumor stages. So maybe there are applications in which convenience sampling is not too bad.
Yeah, so it doesn't mean that your sample is necessarily useless. So, if you're interested in comparing tumor stages, it would probably be hard to think of a rationale as to why your convenience sample would be completely unrepresentative of the population of cancer in terms of differences between early stage and late stage.
So convenience refers to the easiness from a practical point of view to collect the records, or convenience in the sense that the records that you are drawing are easily representative of the population. So convenience refers to what? To the easiness of getting the records, or
yeah, it's sort of
distribution of the population.
I mean, it's a little bit of a I think it was intended as a little bit of an insulting term. It means that the researcher just did whatever was convenient without putting in the effort of what's required to get a random sample. So it just refers to the simplicity of getting the sample, and the typical examples that are given of convenience sampling are giving a survey by standing outside of a store and seeing who will stop and answer your question, or emailing out a survey and then analyzing whoever happens to reply to it, which, you know, those are much easier things to do than getting a list of everyone who lives in your population, taking a sample of them, and then harassing those people in that sample until they answer your questions. So, which, by the way, is what national health studies and that are representative samples do. They make that list of everyone, they make their random selections, and then they go and harass those people until they answer the questions. and in some cases give blood samples and everything. Like, I mean, they can't force them, but they can certainly keep on knocking on their door until, and you know, sending back different people to try and try again until they finally say yes. This is, I think, a really remarkable and underappreciated attribute of sampling, that the size of the population does not matter. So whether you're talking about Italy with 58 million people, the US with 300 million people, the number of people in the population does not enter into any of the statistical calculations that you will use. It's only the sample size. So if you take a sample of 100 people from the US or from Italy, calculate confidence intervals, other statistics, they will be exactly the same in spite of the different populations. And part of the reason for that, or a corollary of that, is that we normally treat the population as infinite. If you have small populations, then the population size may matter. If, you know, you have only 50 or 100 people in the total population, it will matter, but we're never going to do real analyses for such a small. In your analyses, they will, I think, always be based on the assumption of an infinite population. Is this surprising to you? I remember this being quite surprising to me at some point, you know, and wondering why. Like, I remember, you know, when I grew up in my rural province in Canada, and there were political polls, they would take a sample of 1,001 people in order to provide a certain margin of error on the polls. And then you look at national polls in the US, it's still 1,001 people that they use. They don't take a larger sample because they're trying to cover such a larger area and larger number of people. It, of course, may be more challenging to get a representative sample in the larger population, but as long as you take the pain of getting a representative enough sample, then all that matters is your sample size.
So that means that it doesn't matter even when you want to compare these two.
That's right.
Distribution.
That's right. Even if you wanted to compare two, potentially, you want to compare the populations of Italy and the US, you're not going necessarily to take a larger sample size from the US because its population is greater. You most likely would take an equal sample size from them both. And yes, it doesn't matter that one population is larger. Yes.
Is it correct if I roughly estimate my error on my data set, like using the formula of the relative error, which is 1 divided by the square of n, where n is the number of my samples? Can I like estimate roughly that I would have like 30% of error if I take like a population of 10 people? Or is it bad approach? I mean, just to have an idea of how many samples do I need in order to reduce the error as much as possible.
Those calculations, so calculations of sample size and standard error, which we will get to today, are only based on assumptions about the population parameters, not the population sample size, and calculations based on your sample size. So you have the number of people in your sample. If you can change that standard error by changing your sample size. I'm not sure if is that what you were asking?
Yeah, more or less, yeah. I mean, it's not depending on, it's depending on the distribution. I can have like, so it's not always true that I say that whatever data set I'm using, if I have 10 sample, I can roughly say that I will always have 33% of error.
That's right. So that correspondence between sample size and your margin of error, it will depend on your population parameters, like on the standard deviation in the population, but not the size of the population. So in real life, this is what sampling tends more to happen. Even the most diligent, painstaking sampling, where we have the universe, our theoretical target population. So maybe this is, if we're publishing a paper on brain cancer, this universe is all past and future patients of brain cancer. And then we have our empirical target population, the ones who we are actually able to sample from. These are the ones with non-zero sampling probabilities, which we call the sampling frame, the ones that we're actually sampling from. Maybe this is the population of who use a particular hospital when they get brain cancer, because we only have access to the biospecimens from that particular hospital, and perhaps that population is representative of the universe, but it may differ also in some ways. If, for example, the treatment practices are different at this hospital than at other ones, or maybe the exposures, the genetics of those patients differ in some ways from the rest of the population. This is a kind of a question that comes up in meta-analyses, which I do a lot of when you try to integrate results across numerous studies, which may have had different study populations or empirical target populations. And there are people at extreme ends of the spectrum of how to deal with that. At one extreme is sort of the studies are like snowflakes theory, where you just consider that each of these studies are they have different populations, and you cannot compare the results across them. I think that if that were the case, then there would be no point in doing science. You have to hope and try to demonstrate that there is equivalency across these populations, at least somewhat. And then I guess the other extreme end of the spectrum would just be making the assumption that all of these study populations are representative of the same universe of population. So from this sampling frame, you select a random sample. Quite likely you lose some of them due to non-response if this is an observational study where you have to get participation from the study participants, or if this is, I don't know, if this is a trial where you are trying to recruit the participants from your study population, some people refuse to participate or don't give consent to use their specimens for research. You have some loss, and then what is left is your actual final sample. And the impact of that loss is going to depend on whether they were lost at random or somehow systematically different from the rest of your sample. And this is the way the world works. Almost every study, unless you are dealing with cell cultures or something where you have complete control over your specimens, there's likely to be some selection bias in your study. And this is part of the reason that I think myself and many other people advise not taking your statistics too literally and understanding them as a summary of your data and estimate inference on a population, but where there are likely to be a lot of issues besides those that you can account for affecting the results that you have. And just as a pictorial of why selection bias can be important, inferential statistics works by taking a population, drawing some small sample from it, and then performing inferential statistics on that sample, where everyone who is sampled is assumed to represent some larger number of people from the population. So if it's a simple random sample, and you've drawn 0.1% of your population, then every person in your sample is going to represent 1,000 people in the population. So if you have some of your individuals deciding not to participate, or you lose their data or something like that, you've lost a much larger number of people from this inferred population. And if there is bias in how that dropout or that any kind of selection bias, then you can systematically lose parts of your inferred population.
Is there a way to quantify the selection bias? So,
good question. Are there ways to quantify the selection bias? And there are. Well, the most important and simple quantification you can give is to try to quantify the amount of dropout you have. To try and quantify, if, for example, in this step, quantify how much loss you had. So if you drew a sample of 100 and only 60 of those people agreed to participate in the study, you can say that you had a 40% loss. From that, it's not easy to say what effect that has on your results, unless you have enough information about those non-response to say whether it is a random loss or a biased loss. In the worst possible case, where it's a completely biased loss, you can put up on how much effect it has on your inference just simply by assigning them all, for example, to one of your groups or to the other, assuming that it's a completely biased loss. But in general, it's very difficult to say how much effect it has on your results. There are, again, some kind of I guess, culturally acceptable amounts of non-response. So for health surveys where you do a random sample and then people until they agree to be part of your study, if you can get a 75% response, that's considered pretty good. 25% loss. There's still obviously potential for bias in losing 25% of your sample, but it's something that you would probably then accept as the best that you could do. But listing that as a shortcoming of the study and saying that perhaps in some other population where there's a different pattern of non-response, you could see different results.
But also those who respond can bring to a selected bias, no?
Yeah, and I mean it's two sides of the same coin in that if there is a pattern to those who did not respond, it implies that there is a pattern to those who did respond.
For example, to check if there is selection, you should know a priori some features which are correlated with your objective. Let's say you know which is the distribution within the population, the theoretical population. You check if the distribution of these attributes is similar in your sampled records. If not, then you are doing a selected a biased selection.
Yeah, so this is an example of how if you have some information about who was lost, you could be not certain, but you could do some analyses that would give some indication of whether it's or not. I mean, if you're talking about, you know, a population of people and you see that among the people who dropped out, they're all younger, or they're all actually, I think a common kind of non-response is that you can have older, less mobile, potentially less healthy people not responding just because it's more difficult to them. So if you see some kind of a pattern like that, you could suspect that you're having an underrepresentation of older or less healthy people. It's a very common bias in health studies that people who are healthy and interested in their health are more interested or are more likely to participate in health studies. So now we know about sampling from populations. We can talk about the result sampling distributions and the central limit theorem. So I think that intuitively you probably have some understanding of what a population distribution is. This is like a distribution of test scores, a distribution of ages, weights, heights, whatever. This is a probability distribution of individuals in a population. A sampling distribution is far less intuitive because it doesn't represent individuals, it represents samples. So to generate a sampling distribution, you first take a sample from the population. So you're not talking about an individual, you're drawing a random sample from the population. You calculate some sample statistic, quite commonly the mean, if it's a continuous variable, and then you repeat. And then the distribution of those sample statistics forms the population distribution. So just think about that for a moment. We're talking not about a distribution of individuals, we're talking about a distribution of sample statistics. So how is that different from a population distribution? It's different in a couple of ways. Any suggestions?
Size of the sampling.
The size of the sampling. So this is an important way that it differs in that it depends on sample size. So from the same sample population, or from the same population, you can get a different sampling distribution depending on the size of your samples. It's changed about the individuals in your population. If you go from samples of n equals 10 to samples of n equals 20, you will get a different sampling distribution. So that is one way that the sampling distribution differs. It's not a property only of the individuals in the population, it's also a property of your sample size. Anything else?
Combined with the number of times that you repeat the sample.
No. The sampling distribution would actually be based on an infinite number of repetitions of the sampling. So it would give the probability distribution of sample statistics for an infinite number of samples. So it's not the number of samples taken. I'll tell you a couple more ways that it's different. One is that the population distribution is a description of individuals. If we're talking about people, it has to do with individual properties, characteristics like height, like weight. The sampling distribution does not. It's a property. If we're talking about mean, then it is a distribution of averages. So it does not. It is affected by individuals in the population, but it's a property of groups. So that's a very important thing to understand about sampling distributions, that for the statistics that you will use, sampling distributions are about average properties. It's just about the average. One third way, maybe, that sampling distributions differ from population distributions is that almost always in your data sets, in your studies, you will only have one sample. So whereas if you have a sample size of 100, you could get an idea of the spread of let's say of weights of study participants, but you only have one sample. So you can't get any kind of an estimate about your sampling distribution because you only have one sample. So if you take, just to say that again, if you have a sample of n equals 100, you have 100 individuals, which you could use to make some approximations about the study population, but you only have one sample. So if you calculate a sample statistic, like the mean, you just get one estimate of the mean. So you're not taking multiple measurements along that sampling distribution. And this will, I think, become more obvious and be important to realize when we do inference.
When I do sampling distributions, as I understood correctly, I like, I don't know, shuffle the population, take out, I don't know, 10, 20,
Mhm.
do the statistic like the mean, and that's my first number. I
Yeah.
do this 1,000 times, and then I have 1,000 things to plot and see the
Yeah.
distribution of that, which implies that I can take the same samples multiple times.
So this is, you're jumping ahead to the Monte Carlo and permutation tests. Yes, these are ways to using a computer to simulate taking multiple samples, which we will do this afternoon. So that you can use to do things, for example, like generate a distribution of statistics under the null hypothesis. But there are ways of simulating that. You still have one sample. So as in terms of your average, you still only have one average for that sample. You can permutation test to see what the distribution of them would be under the null hypothesis. You can use a bootstrap to get an idea of the variability of that from your sample size, but your average that you will use for inference, and that will be your best guess of the average in the population, you just have one of them still. But these simulations are very useful, I think, for understanding sampling and sampling distributions, because when you only ever deal, like when you do your data analysis for a study and you do your t-tests or your whatever tests, it can be kind of easy to lose sight of the fact that you just have one single sample from that your 100 samples don't represent, or that they're not, they're not your complete population, and all of your calculations are approximate from it due to sampling variation.
So I will never do in my lab the sampling of the sampling. I will have just the data that will arrive, that will be my sampling.
That's right. That's right. The data that arrives, that will be your sample. And in some cases, you might split it into another sample for training and testing or things like this, but you're never going to, even if you do that, maybe you have 2 samples, right? You're never going to have 100 samples or something like that. It's not the way study design works. So remember from last class, our example of observing 100 counts from a Poisson distribution. The Poisson distribution just has one parameter, lambda, and that lambda defines both the mean of the population, number of counts, and the spread of it. And recall that Poisson distribution can be useful. It's for count data, and it's useful when you have a number of low probability independent events, such as the number of ambulance calls coming into the, what was it, the 822 center? The
82%. 82, what is it?
118, sorry. Yeah, I just learned that if I'm in trouble here, I should not dial 911 because it won't work. So the number of 118 calls received in an evening is often Poisson distributed. So the Poisson distribution is completely specified by this one parameter lambda. We drew 100 counts from that distribution and made a bar plot, and then overlaid it the population probability distribution. So my first question looking at here is this Is this a population or a sampling distribution? So you're seeing a probability distribution here in terms of frequency rather than probability, but you could just divide this by the total by 100 and it would be probabilities. So is that a population or sampling distribution? This is your test because I spent quite all that time explaining the difference between population and sampling distributions. I want to make sure you'll be able to distinguish them.
It's a sampling distribution.
Why is that?
Because we are observing 100 counts, but from a Poisson distribution. So this makes this graph, I mean, these histogram values are coming from a Poisson distribution and
Yeah.
more from individuals.
Yeah. So it's a what? So what is it?
A sampling distribution.
No, your explanations were all right until you said sampling distribution. So you're looking at a population distribution because you're looking. This 100 counts as one sample. So when you take a sample and make a histogram from it, it's only an approximation of the population distribution, but it's an approximation of the population distribution, not the sampling distribution.
It's so the entire plot.
Mm-hmm.
But I see there seven histograms, so 7 bars.
Yep.
I assume that every bar is like 100 things that I sampled from the real population.
So this in the ambulance case, this would be like we looked at the records of the number of 118 calls over 100 nights. On 10 of them, there were 0 calls. On 27 of those days, there was just 1 call. So
I thought that every single bar was 100.
Yeah.
oh, okay.
Yeah.
Sorry about that. No. This is I'm actually in upcoming slides going to show you what happens when we do that. It would no longer look like a Poisson distribution because the sampling distribution, it turns out, is no longer Poisson distributed. So this could also be, another example would be, let me think. Another example could be I suppose it could be an RNA-seq experiment, and these are 100 genes, and the number of reads we observed for each of those 100 genes. That may be Poisson distributed, or more, probably more to the point for this would be it's just one gene of interest, and we have 100 patients where we've done our and this is the number of reads for that gene observed in each of those 100 patients. So we have 2 patients where we got 2 reads, 2 patients where we got 5, 11 patients where there are 4 reads, etc. Does this make more sense now? And if we were to somehow continue this experiment for an infinite number of patients, and the distribution of the number of copies of this gene that we see as Poisson distributed, then eventually it would exactly reproduce this Poisson distribution, which is the distribution of counts of that gene in the population, the entire population of patients, or the distribution of the number of 911 calls made on a given night across all of time. So this is a population distribution. In general, these exotic distributions, Poisson, negative binomial, these are population distributions. When it comes to sampling distributions, there are a much smaller number of them that we actually use. Okay, so here, let's do it differently, and we can do this because it's a computer. What was on the previous page, those 100 different counts, I calculate the mean of them, and then repeat that 1,000 times, and I plot all of those means. Here's what I get. So is this a population distribution or a sampling distribution? Is it clear what I'm doing here? Yeah, I calculated the mean of those counts, and then I just repeated the experiment, the sample 1,000 times. So yes, this is a sampling distribution. And what do you notice about it?
Because it's we are talking about the means
Yes,
of the 100 counts.
that's right.
That's different because before, earlier we said that those 100 counts comes from maybe just individuals selected by parameters and clustered somehow. That's different.
Yes.
The comparison is clear.
Yeah. And so in terms of properties of this distribution, what do you notice? Here, I'll show you the previous one and this one. There are a few differences here. Some of them are easy. This is going to be a prelude to the central limit theorem.
It's symmetric.
It's symmetric, yes, that's a very important one. So whereas this Poisson distribution, the population was asymmetric, it's skewed to the right, this one looks completely symmetric. Anything else?
Before we had just values for integer number.
Yes, so here we have only integer values. We have now a continuous distribution. We have a continuous range of values because we are calculating means. So, so even though it was a count distribution, our sampling distribution is continuous. It's not only integers, which is kind of convenient.
I have more a question than an answer.
Mm-hmm.
That it's not true that if I have like some kind of phenomenon that I say that it follows the Poisson, if I do this sampling distribution, it will still be a Poisson. This is the Gaussian. Okay.
It turns out this is Gaussian. It's not Poisson.
Okay. So, so what makes that a Poisson? Or why then that was? What was the mistake that led us to say that this was a Poisson?
It's not a mistake. It is Poisson.
It is a Poisson, but if I start to do repeat it turns to be a
Frequency.
Yeah, surprising, isn't it?
No, it's the center.
Yeah, it's very surprising. It's very, very surprising. And I'm glad you find it surprising. Yeah, we have a Poisson distributed population, but when we plot the averages, it's not Poisson. It looks Gaussian, normal.
And also, the frequency in this case is much more higher.
The frequency? Oh,
yeah.
Yes, yeah. The frequencies are higher because I took 1,000 samples just to make it fairly smooth. Yeah, that I could have I mean, I could change the frequencies by changing the number of samples, but yes.
So is this a proof that we basically are looking at two different objects?
We are looking at two different objects,
Even
yes.
if we are trying to investigate the same phenomenon, those are completely
Yeah.
different.
That's right. Yeah, and we'll formalize this a little bit later with the central limit theorem, but there is reason that these look different. It's a very surprising result of statistics, and also a very general one. It turns out that if you are drawing reasonably large samples, not even huge samples, just, you know, and more than 30 maybe, or a little more than that, then it doesn't matter what distribution your population is, you always get this Gaussian sampling distribution. It's super surprising.
Is it also the interval more narrow?
Yes, so very good observation. So you notice here that the interval was from 0 to 6. And here the interval is only from 1.6 to 2.4, or 1.5 to 2.5, a much narrower interval. That's an important observation. And this is because, this is, I think, a more intuitive understanding that individuals, you know, they're individual. They can differ a lot from each other. But groups, their averages tend to be not so different. So, you know, for all sorts of properties, it's very general. It doesn't matter what it is. You can have a lot of variability among individuals, but the larger the group, the less difference there's going to be among their average characteristics. And this is a property of the sampling distribution. The larger your group, the less variability there's going to be among those averages. And maybe only one more thing that I will point out is that the average is 2. So remember the theoretical distribution that we used had an average of 2, even with all of this skew. But this is bearing out that the averages of all of the samples is centered on 2. Which brings us to the central limit theorem, which is how we can explain these phenomena. So the central limit theorem, it relates the sampling distribution of the means to the population distribution. That's what we use it for. And it comes in 3 parts. The first part is that the mean of the population and the mean of the sampling distribution are identical. So this was that last observation that I made, that these two distributions, even though they may differ in shape, they have the same means. And of course, we're talking about the sampling distribution here. So if you take just a single sample or you take a handful of samples, the means will not be identical. There will be some random differences between them. But if you build a sampling distribution from a very large number of samples, the means will asymptotically become identical. The second part of the CLT is that the standard deviation of the population is related to the standard deviation of the sampling distribution, which is also called the standard error by this relationship, that the standard error is equal to the population standard deviation divided by the square root of the sample size. So this formalizes that, that intuitive observation that we made earlier, that the variability of the sampling distribution was less, and also our intuition that a groups of 3 might be more variable than groups of 1,000. That the larger your samples get, the less variability there will be among their average characteristics. And then finally, for large sample sizes, the shape of the sampling distribution of means becomes normal, regardless of what shape the population distribution has. This is a very important result, and one that will have, all of these have practical implications for your data analysis. So these are the 3 components of the central limit theorem. There's just 3. I'm going to demonstrate them to you. This first component of equal means, using the example that we looked at in detail, our one sample of 100 counts. It has this skewed kind of distribution, but the mean on average is going to be 2. If we took a sample of 1 million, it would be 2.000 something, but in the population, the mean is 2. For these, for the means of the samples, as we saw, we have a different distribution of the means, but the mean is also 2. The standard error is equal to the standard deviation of the population divided by the square root of the sample size. And the effect of this we can look at by plotting the distribution of means. So I'm drawing 1,000 samples of size n equal to 30. And here is the amount of spread we have from about 1.4 to 3. Then I do the same thing again with samples of n equals 100. Again, I'm calculating the average in each of those samples and then just plotting them. And I'm using the same axes, the same scale on the axes here. You can see it's getting narrower. If I increase my sample size to n equals 500, it's narrower still. So this is the reason why in general we can make more accurate inference from a larger sample than we can from a smaller sample, because what this represents is sampling variability. If you draw 2 samples, you will get different averages from them, but if they're larger samples, that difference is going to tend to be smaller. They're going to fall within a smaller range due to random sampling variation. It is important to note, and I'll probably try to hammer this in again later too, however, that your inference from a small sample is not any less valid than your inference from a large sample, because the techniques developed for statistics are to formalize the variability that comes from sampling. So if you, and that is formalized through things like p-values and confidence intervals. So if you have a sample size of n equals 30, you will get a larger confidence interval than if you have a sample size of n equals 500, but it doesn't mean that that confidence interval is any less valid. In fact, the opposite could be true. If you have a large sample but a biased sample, you will have a smaller confidence interval, but it may be less valid than the larger confidence interval from a small but representative sample. This is one of those things people talk about in big data, like how many observations do you need to have to make it worth the bias that may come with that large sample? It's a good question. And the third part has to do with large samples, that the distribution of means from large samples is always normal, regardless of the population distribution. So how big is big? And there's no real answer to that, but I guess here are some rules of thumb. If you have a sample size of less than 30, then it's still okay as long as your population is normal or very close to it. If you have a sample size of more than 30, this is generally considered a large sample, and even skew and some outliers are okay. And then if you have n greater than 500, that's quite a large sample, and really even pretty extreme population distributions are okay. That's surprising too, isn't it? That n equals 500 is a very large sample size. It's certainly, you can, I mean, for anything greater than n equals 30, you can be fairly comfortable using the central limit theorem and the tests that result from it. And for anything more than n equals 500, absolutely, you can use the central limit theorem and be confident in arguing back to any reviewer that says, but is your population really normal? You can say it doesn't matter. So here's an example. I generated an extremely skewed distribution. This is a log normal distribution, which means that if you take a log of the values, it results in a normal distribution. So it tends to be extremely skewed. Here's one sample of 100. You see most of the observations are almost right down at 0. The mean here is 1 in this distribution, but you have values going all the way up to 40. And then I've drawn two sampling distributions. One is for n equals 30. You can see there's still a bit of skew in here because it has such an extreme skew in the population. And here with n equals 500, you see it basically looks normal. This is, maybe there's a tiny bit of non-normality, but it's pretty close. All right, and the last part of class today is to introduce, lecture anyways, to introduce the t-distribution. And what do we use it for? So we're calling again from the central limit theorem. The sampling distribution for large samples, regardless of the population, has a standard error. This is the variability of the sampling distribution of sigma population standard deviation over square root of n. When you have a normally distributed population, that is true for any n. It's true for n equals 1, n equals 2, any n. And for non-normally distributed populations, it's only for large n. But that's assuming that we know sigma, the standard deviation in the population, which normally is not the case. Normally, we're going to have to estimate the standard deviation from the sample. So you're going to have your 30 individuals. You're going to estimate. The standard deviation, and it turns out then that distribution has wider tails than the normal distribution. And just to show you what that actually looks like, I've plotted here a normal distribution with mean 0, standard deviation 1, along with several t-distributions for differing amount of degrees of freedom, which I'll talk a little bit about later. But generally, degrees of freedom correspond closely to your sample size. So 15 degrees of freedom, probably a sample size just a little bit greater than 15, and you see something very close to the normal distribution. And then down to 7, you see the tail getting a little bit larger, and for 3 degrees of freedom, the tails are a little bit fatter still. So why would such an apparently small departure, like visually it doesn't look like too much, why would that matter? Think about I know we haven't covered hypothesis testing in terms of probability distributions yet. But when we do hypothesis testing, we're going to be calculating the probability in the tails of this distribution. So yeah, so it can change your probability of accepting the null hypothesis. And even what looks like a small difference here, you can imagine that once you're out in these tails, this is actually quite a large difference. At this point, beyond 4, the probability is much, much greater for this t distribution with 3 degrees of freedom than under the normal distribution. So when you're doing inference, this difference can be very important, or when you're doing hypothesis testing. So when we use the t distribution, we're going to calculate a t statistic. There are some different t statistics that you'll calculate. This is a one sample t statistic where you've drawn one sample, you've calculated from it a sample mean, a sample standard deviation, and then we want a statistic that will describe how different this sample is from a hypothesized population. So this hypothesized population, what we will eventually call a null hypothesis, has a mean of mu0. Then our one sample t statistic will be the mean of this sample divided by the theoretical mean under this null hypothesis and divided by our our estimated standard deviation from the sample. And you can use this if either the population distribution is normal or you have a large sample size. And you notice I say here, if you have a large sample size, I'm actually not recommending that you use the central limit theorem, which would say you have a normally distributed sampling distribution. You would still use the t sampling distribution for large sample sizes if you're estimating the standard deviation from the sample. Because you remember from the central limit theorem, the standard error was sigma, the population standard deviation over square root of n, but we don't have sigma in this case. We only have this s that is an estimate from our sample. That is the key attribute of when you use the t distribution as opposed to a normal distribution from the central limit theorem. It's when you're estimating the standard deviation from your sample. Then this t statistic, this is for a one sample based on the means and standard deviations from a single sample, is t distributed with n-1 degrees of freedom. Different uses of different types of t-tests will have different degrees of freedom, but for one sample and its mean and standard deviation, it has n-1 degrees of freedom. And this will lead us to the one sample t-test. and we will get into hypothesis testing in the next class. And just as a note, that when you take two samples and calculate instead of just the mean of one sample, but the difference in means between two samples, that also turns out to be t-distributed when you're estimating standard deviation from the samples. This is the final slide for today, and I'm just going to give some motivation for hypothesis testing, which will begin next week, and note for you just that it is not the only framework for inferential statistics. There are also confidence intervals, which are preferred by many people to hypothesis testing, reporting of posterior probabilities, the probability of certain things being true, which is an outcome of Bayesian statistics. And I provided a link here to a paper. P-values are just the tip of the iceberg, which I would recommend you read. It's an easy read. It's just a couple papers. It's in Nature, and I feel that it's important for you to know, both as you learn about hypothesis testing here and as you apply it in your lab, that there are a lot of criticisms of the very bases of hypothesis testing that you at least should be aware of, and not treat your hypothesis tests as the absolute truth or the only way of doing things. Okay, we have a couple lab exercises to do. There's actually something that I wanted to do quickly before we start doing those, but there are the links, and also links to today's materials. I'm going to stop our recording now.